Okay, once again, welcome back, folks. This time around, I'm dealing with connected particles. As you can see on the screen, we've got a zero point um, object as well as a zero point 0.1 kilogram object. Both these objects they are suspended some 8 meters above the ground. Let's try and read the story and uh, listen to what the examiner needs us to do. Um, so going through the story with two particles A and B, direct masses 0.3 kilograms and zero point 0.1 kilograms respectively. The particles are attached to the ends of the light inextensible string, means it doesn't stretch. String passes over a fixed smooth pulley and the particles hang vertically below the pulley. Both particles are initially at a height of x meters above the ground. See the diagram. System is released from rest. So now, the moment they enter off rest, we know the initial velocity of the whole system is zero. But what we know, going downwards here, we have got weight of the object is going to be 3 newtons because it's 0.3 times 10. And for this particle, it's going to be 1 newton because it's 0.1 times 10. Now, we are required to find the tension and acceleration of the particles. But what we know is tensional force is going to be going against, for the first object, against the weight, and with the second object, its tension which is pulling the system upwards. So now, according to Newton's second law, we are going to be interested in saying, for particle, let me call it particle A. This is what we observe, that the weight is the one which is pulling. And what does the Newton second law say? It says F equal to ma. So the moment we see A, we should think of the equations of motion. We shall, at least should we need them in the problem. So let's take a look at what's happening. The net effect here is 3 minus t equal to ma, that's 0.3 a. Now, when I go to b with the same thinking, I'm going to see that not it b actually is the tension minus the weight, which is 1 equal to 0.1 a. Now, if you check, we've got simultaneous equations that can help us to get the unknown value of either a or t. But I think it's wise for us to eliminate t first. So I'm rewriting these equations below. So we have 3 minus t equal to 0.3 a for the first object a. And I've got t minus 1 equal to 0.1 a. Now, when I sum a line which is acceptable because both equations have same variables b and t, what it implies is these two are going to cancel. And when I say 3 minus 1, I end up getting 2 being equal to, when I sum these two, I get 0.4 a. Then if I divide both sides by 0.4, I think I'll end up having the magnitude of A as, let me bring my calculator. Here I'm saying 0.2 divided by 0.4, it will give me, sorry, let me redo it again. 2 divided by 0.4, this will give me 5. So it means for the whole system, the acceleration is 5 meters per second squared. Now, once I get the value of A, it means I can easily get the value of T. Then with any of the two equations, let's say I pick this one here, I'm saying T minus 1 equal to 0.1. Instead of A, because I found A, I'll say multiply by 5. So if I multiply 0.1 by 5, I'll get 0.5. So my T is going to be equal to 1 plus 0.5. So my tension is actually 1.5 newtons. In other words, it's for the first part. Then moving to, we have the second part, let's check. Oh, there is a second part. During the subsequent motion, B does not reach the pulley. But when A reaches the ground, it comes to rest. Given that the greatest height of B above the ground is 1.2 meters, find the value of X. So we are told actually that the highest point reached by B is 1.2 meters above the ground. But now, coming back to the system, we can see clear that in this system's motion, this part here is x, and as A travels to the ground, we are going to also cover another x. But now, this is what happens when A reaches the ground. There is a slight motion upwards that B undergoes. Our interest is to find that motion. But now, what do we know? We know that when A is going to the ground, its acceleration is 5 meters per second that we learned earlier in the calculations. So A is 5, and what we know initial velocity was 0, and also the distance to be covered is actually x is now. What's our interest? Our interest is to know the final speed. So with those things in mind, going to rewrite them below so that our calculations are needs. We're saying initial speed is 0, our acceleration is 5, and s the distance is x to be covered. So we are interested in the variable value of v. Now, if we look at the variables that we have there, there's no time. So we can easily use one of the equations of motion. I'm glad that the second one said v squared equal to u squared plus 2as. So I'm interested in the final velocity. Now, when I put my u, it's going to be 0. So in essence, I'm saying v squared is equal to 2 multiplied by 5 multiplied by s. So this will give me 10s. So in essence, v is equal to root of 10s. I will make v. But now, coming back to our problem, we need to appreciate that that happens when the object b is at this point. So at this point, we can come to say, but the initial speed is going to be with 10s. Now, because object A we have reached the ground, it means there is no more rotational force forcing the object upwards. And somewhere in the motion, because there's no more force, is going to have a final velocity of 0. Now, the question is, what will be the acceleration be going to have an acceleration and the final velocity of 0? Yeah, because we have killed this. Initially, it was t minus 1 equal to 0.1 a. So we'll come and say, somewhere below here, or you can do it aside to say t minus 1 is equal to 0.1 a. But remember, when object A reaches the ground, this is gone. So we can safely say for A, this is going to be negative 1 divided by 0.1. In essence, A is going to be negative 10 meters per second squared, which is something that we need on our equation above, where we're saying for objects B, we have got B equal to 0, U equal to, and our acceleration B equal to negative 10 meters per second squared. So what do we want here? We are interested in S, the distance that it will cover. So with that in mind, I'll come down and say, all right, I've got a final velocity of 0, initial velocity of root 10, equals root 10 s. But I guess it's not to be x because that's the distance that it covers. But then our acceleration is negative 10. So what we want is the height sorry, the height s. So we are going to bring back again the same equation we used to say, but v squared is equal to u squared plus 2s. But v is 0. What about our u? Our u was 10 s. Oh, it next to this x that we saw on the diagram. So that we multiply by 2a, but a is known is negative 10. Variable is actually s, which we need to say how much distance does it go up. So if I rearrange, it means I have 20s equal to 10x. So that short distance that s, I mean, object u will travel and that was set by 20, like this. This will cancel, so my is going to be 0.5x. So going back to our diagram, we can now clearly see that, we can clearly see that this object B, it moves. What we're interested in besides about the ground, there is x, but it will also move another x. But when A reaches the ground, it will move slightly 0.5x. So if we sum up those three, that should be equal to 1.2, which we're given there. So we can say we come back and check is 0.5. Well, it's actually x. Sorry, x. So come and say x, which is the initial height above the ground, plus another x when object A travels down, plus 0.5x. This should give us a total of 1.2, which is the greatest height that's reached. So I want to find x. So when I sum the left side, it will give me 2.5x equal to 1.2. When I divide both sides by 2.5, um, the result that I'll get is my x. Let me bring my calculator to say 1.2 divided by 2.5. Let me turn it to the decimal. It's going to be 0.48. So x is actually 0.48 meters. I hope you guys found this interesting. There's connected particles and the maximum height that an object reaches as it travels high up the pulley. Thank you.